All right, welcome to Precalculus. Today's date is the 7th of March, so it's 7/3/2023. We're doing a Zoom lesson because Mono City kids have been trapped due to avalanches. Let's go ahead and begin. By the end of this lesson, I want you to be able to solve an exponential equation that is hard and requires logarithms. So you'll solve something like 5 to the power of x is equal to 86, something like that. Like, how do I solve for x? How do I get untrapped out of the exponential? The easiest way to teach this is to do an example. So let's go ahead and just jump straight in. We do need calculus for this lesson, which is why I have that calculator over to the left. We'll do example number 1. Example number 1, I'm going to say, I don't know, choose a number, Emma.
5.
5 to the power of x is equal to, choose a number, Diego.
2.
Sure, yeah. There it is.
I'd probably pick that.
No, no, like they're going to be hard no matter what. I was thinking like of a big number, but that also works. So I can solve this, but I need to know how to use logarithms.
Oh, so there's no y involved.
Nope, I'm just solving for x. All of these are how do you solve for x? And again, you're going to round to 3 decimal places. I think the homework rounds to 4 decimal places on every single one of them. Yeah. So we'll practice running 4 decimal places. How do we do this? There's only one tool that will move our exponent down here. There's only one thing in all of mathematics that will do that, and it is called the.
Oh God, I am. Okay, give me 1 second. Let me.
Giorgio, come on, help me. What is it called? What's the thing that makes this go down here?
The root. The root.
Close.
No, wait.
Is it? I don't know. Is it the?
Log.
Yeah, it's a logarithm. Giorgio knows. Okay, cool.
That was gonna be my first guess, guys. Don't worry.
That's totally what I was about to say.
So what I'm going to do is I'm going to take the log of both sides. So I'm going to say the log of the left side is going to be equal to the log of the right side. So the left side used to be 5 to the power of x. The right side used to be 2. So what I just did there was I took the log of both sides. And the thing is, I can choose any base I want. That's kind of the fun part about logarithms, the reason that they're so valuable. Do you guys remember how to take the inverse operation of exponentials from 3-6, 7 or somewhere around there?
Sure, yeah, you have to use the same number.
Yeah, the same number. So should we use 2 or 5? Do you agree or disagree?
I actually agree.
I agree. Yeah, I agree as well. It should be 5 because if I'm looking at the original problem, 5 was the base, x was the exponent. When I'm doing a base with logarithm, it should be the base of the exponential function. 5 is the base of the exponential function, so 5 is also going to be down here. Let's go ahead and I'll copy down. This can be log base 5. If I do log base 5 on the left, I also have to do log base 5 on the right. Cool. And let's really test Giorgio and Chloe and everyone. What does that left side turn into?
X.
Close.
Log.
No, it is x, isn't it? I think it is exactly x.
Oh, it's just
Because
they cancel out.
yeah, I mean, there's 2 ways that you can interpret it. Here's the way that I always interpreted it in high school. I always said, okay, well, the x now has permission to come down in front. And this can be turned into x log base 5 of 5. You're always allowed to bring down the power. That's one of the properties of logarithms. That's the whole point that we use the logarithm to bring that exponent down. And then I can reinterpret this logarithm. I don't really think of this in my head as a logarithm. I think of this as the what power function. What power does 5 need to be raised to in order to get to 5? 5, what power is 5? 5 to the power of 1, which means this entire thing is 1. And 1 times x is just x, which is what Diego said at the very beginning. This side is just x.
So it's x equals log 5.
There's, yeah. So over here, we can say now this is going to be equal to log base 5 of 2. So x is equal to log base 5 of 2. But I'm not going to rewrite that a second time because calculators typically can't do any other base other than e and 10.
Wait, is it more to this?
What's up?
Is it more to that?
Yes.
Oh my
There's
God.
a little bit more, tiny bit more.
I put the box around.
What I'm going to teach you now is, I'm going to label this out to the side. This is called the change of base formula. Sounds good. Change of base formula. The change of base formula allows you to convert that base of 5 into any base that you want. And because calculators have bases typically of 10, and if you want to use the natural logarithm, a base of e, let's change it into a base of 10, right? Yeah. Here's how you do that. I'm just going to show you, and you guys can probably pick it up from there. This is going to be log base. We choose 10, so it's going to be now base 10. And I'm going to do log base 10 of 2 all over log base 10 of the other number. There it is. It's a change of, that is it. It turns into a fraction, and you get to choose any base that you want. Notice that the base of 5, or maybe I should do this in 10. This base of 5 went down here into the denominator. And this number 2, I guess that's called the argument of the logarithm, stayed in the numerator. That will 100% be the case. The argument is always in the numerator. The base is always in the denominator. And the way that I think about that is when I'm thinking of an exponential function, the base is always on the bottom. It's 10 to the power of x. The 10 is the power, or sorry, 10 is the base of. I'm confusing you guys. Base always goes to the bottom. All right, we enter this into the calculator and we're done. Yeah, Diego.
Why is it 10 out of every number? 9, 7, 11.
Why do we use 10 for calculators? It's a great question. Should I answer? It'll be like a 5-minute tangent if that's okay with you guys.
Tangents attention. Let's hear it.
All right, so we typically use logarithms to talk about size of things. What a logarithm by default does is it counts the number of zeros. So I'm going to go ahead and go on this brief tangent, and you don't have to copy this down for your notes. In the number 10,000, how many zeros are there? 4. There's 4 zeros. In the number 1,000, there are 3 zeros. This is the number of zeros. And this is the number. In the number 100, there are 2 zeros. In the number 10, there's 1 zero. In the number 1, there's 0 zeros. On your calculators right now, type in log of 10,000.
Where's the thousand? 4.
What do you think log of 1,000 is going to be?
3.
What do you think log of 100 is going to be?
2.
Logarithms just count how big things are. How many zeros do you need? When you talk about things like earthquakes, and you're talking about, oh, it's a magnitude 8 earthquake, it literally means you need 8 zeros to measure the size of that earthquake.
What does that measure like that?
I don't know what the units are measured in, but it measures the how much, I guess it shakes, how much power it has. I think it's measured in force, some unit of force. I don't know that much about science. That's more of a Mr. Brown's expertise.
Missed the point.
The strange thing about this is that it doesn't work when you have a leading number other than 1. So for example, if I want to do, what is 20,000? How many zeros are there? And you'd be like, well, there's 4, Mr. Snell. Here's the problem. Because this number is a little bit bigger than 1, this number needs to be a little bit bigger than 4.
Whoa.
So it's gonna be like 4.1 or something.
4.30102.
Yeah, okay. It goes on forever and ever, whatever. But it's like 4.3. It's a little bit bigger than 4, right?
Yep.
So that's what these logarithms do, is they tell you the size of things. So they're really useful when you're working with exponential systems. So if I'm dealing with pandemics, for example, that started out as an exponential function. We needed to use a logarithmic chart in order to plot what was happening, to see if it was increasing at an increasing rate or increasing at a decreasing rate. There's my brief tangent. How am I doing my time? Was that like a 4-minute tangent, 5-minute tangent?
Approximately 4.3.
Yeah. So the point being, the base of 10 measures the number of zeros, because 10 to the power of 2 means there's 2 zeros. If there's 10 to the power of 5 means there's 1, 2, 3, 4, 5 zeros. We choose a base of 10 because that is what it means to have that number of zeros. So I circled all the way back to the original question, hopefully answering it. Base of 10 is the size, and that's the normal base that we use, but it's not natural in terms of the natural logarithm. I can now evaluate this fraction. I just type it in. Are you guys ready? On your marks, get set. I type in log of 2. And then I end the parentheses and I divide that by the log of 5. I'm done.
Whoa.
So I can say that this is, because I'm approximating now, I'm not going to use an equal to sign, I'm going to use a wavy equal to sign, which means, again, this is read approximately.
Oh, my fault.
Approximately. And I'm now estimating 0.4306765. It goes on forever and ever. And we're typically going to round to 4 decimal places. So I'm going to round to those 4, and my answer is going to still be approximately 0.430. Is it 6 or 7?
7.
7, because we're rounding up. There's our answer. That's like a full-on easy problem. Ready for a medium problem, guys? And they all cheer, yay, let's do it.
Yay.
I mean, George is ready. I see him up there.
Yeah.
All right. Would you like me to give you the official change of base formula that you'll see in the textbook, just so you can have that in your back pocket? The change of base formula states this. If you have log base b of a, sure. I was running out of letter. Log base b of a is the same thing as log base anything. I'm just going to choose 10. Log base 10 of a all over log base 10 of b. I know my b is in my 6.
There you go.
There's your formula, and maybe not so neat handwriting, but there it is. So it's a change of base formula. That way you can get to this nice base. You could have chosen E and E. It's the same thing. You'll get the same exact answer, in other words. Anywho, let's go ahead and move on to example 2. I'm going to have you guys choose some random numbers to make a problem with me. Example 2. Example 2. Let's make it a medium problem. Oh no. Shout out a number, Giorgio.
He's dead.
6.
6. We'll make this the power of, we'll make it intermediate. Chloe, shout out a negative number.
-7.
We'll say -7 or -7. And then let's make this a truly, make it slightly more difficult. I'm going to multiply this out front by another number.
2.
2. And I'm going to make that equal to
5.
5. There's a problem.
Number.
All right, I can solve that problem. And it is really hard to do. Like I could not even start to guess. I'm like, here's my guess, 7.2, maybe. I don't know. Maybe like 7.5. It's really hard to guesstimate what X should be just by looking at this. Here we go. The whole first step is to isolate the exponential problem. I'm looking at you, you 2. That 2 right there. I don't want that one because this is the exponential. This 2 is not part of the exponential. You need to first isolate the exponential. So let's get rid of the 2 first. So I mean, if I'm writing out my procedure, step 1 is to isolate exponential.
Isolate exponent.
Because sometimes I'll have this thing is being divided by 3, which takes out multiply by 3. Sometimes I'll have +1 out front, which means you subtract that 1. You need to do whatever it takes to isolate the exponential. In this case, Diego has that first step, which is to
Divide by 2.
divide the left by 2 and the right by 2. So here's our new problem after Diego's first step. Diego has transformed the problem into 6 to the power of x minus 7 is equal to 2.5. Or you can leave it 5/2. Actually, I prefer fractions, but just to keep everything on the same line, I change it into a decimal. We have now isolated the exponential. We have now done step number 1.
That is 2.5.
Okay. You learned something new?
That's all I was gonna do.
That's why he comes to school to learn things. From here, the exponential is isolated. So step number 2, if I'm being very explicit in my procedure, is to take a logarithm of both sides. Log both sides.
So it's gonna be log 6 to the power of x minus 7.
Log and then of that 6 to the power of x minus 7, you're right,
And this is n equals log of 2.
exactly, log of that 2.5. All right, and again, we get to choose any base that we want. We'll give it to the zoomies. Between Giorgio and Chloe, what should our base be for both sides?
Am I allowed to just say 10?
Sure, yeah. You can say 10, but that won't work very nicely because what we did in our last problem is we chose
2.
5. Because if we choose 5 here, you'll get a double 5. And what power does 5 need to be raised to get 5? 1, and it cancels that whole thing out. So be careful and choose a nice number.
I'm gonna say 2.5 to get rid of the right one.
That would be nice because that will get rid of the right. And unfortunately, you'll still be left with a lot of like we're trying to make the side with X to be as nice as possible. So you are right. That will make the right side really nice. But I want to make the left side really nice because it's going to be really hard to isolate that X. So I think it's, I mean, we can go with your logic. I haven't done it that way. Should we just investigate what would happen?
You don't have to.
I'm trying to predict what would happen. 2.5. You'd need, yeah, it's gonna get really nasty because you'll have to do a change of base on top of a subtraction problem. It gets really, really gross. I mean, this problem is gross by itself, but the way that you're doing it is gonna make it really, really difficult. I'm gonna just show you the easiest route, and then hopefully that'll help everyone from there. The easiest route is to choose the other base, Giorgio, which would have been what?
6x minus, yeah, 7, just 6.
Choose a base of 6, because what will happen now, this x minus 7 comes down in front, become x minus 7 times all that other stuff. Log base 6 of 6. This is going to be log base 6 of 2.5. All right, other zoomy, Chloe, what is log base 6 of 6?
1.
Excellent. So this is all an arrow that goes to 1, meaning the only thing that we have on the left side now is x minus 7. It's kind of nice. That simplified quite a bit. I had this really trapped exponential, like our variable was up in the exponent. That was really hard to get rid of, but now it's down here in the base. It's really easy to work with. It's back to algebra 1. Unfortunately, this right side is kind of disgusting. Let's go ahead and use a change of base formula between Diego and Emma. Who wants to try the change of base formula on this thing? Because I can't punch this into a calculator yet.
So it'd be x minus 7 equals log of 6.
Log, I want a nice
Log
base.
base.
Log base 10.
Oh, just got it. Log base 10 of 2.5.
Good, of 2.5 divided by log base 10 of 6. Whatever. There it is. And we have one final step, Emma. What do we do to both sides? Get x by itself. Add
7 to both sides.
Add 7 both sides, and here's my final answer. X is equal to 7 plus this fraction, log of 2.5 all over log of 6. And I just typed that into my calculator over here, and we'll see what we get. 7. Oop, is that right? 7 plus, it's gonna be a fraction here. It's gonna be log 2.5 divided by log of 6. You guys get that on your calculators as well?
Yes.
All right, so we are now approximating, so I'm doing a little wavy equal sign. 7.511391594. But again, we're only doing 4 decimal places in this whole unit, so I'm gonna go ahead and look at. That was not what I want to do. So I didn't even do 4. 5. There we go. I'm running there. Does that 5113 stay at 3 or does it turn into a 4? All right, so here's our final answer. Our final answer is going to be 7.5114 for our final answer.
It's not too
I mean, I can either show you guys a really hard one, or we could just jump into class.
password.
I mean, they're all the same steps. I mean, here's step 3, which I didn't state explicitly. Step number 3, solve. And then usually there's change of base needed. Perfect. So that's all the steps. There's our notes for the day. How do you guys feel about this one? I'm looking at the Zoom kids screens right now as well. And if this is 5, how well do you think you could solve a problem that was an exponential where that variable is trapped in the exponent? I'm seeing 4.5, 5. I'm seeing Giorgio at 4 and Chloe at a 5. All right, let's go ahead and move into the classwork and I will stop the recording.
And just, are we gonna use the